Hi, this is part 2 of a 3-part video series looking at the Raspberry Pi with Windows 10 for IoT and the DAC8734 digital to analog converter from Texas Instruments. In this particular video, we're going to be looking at the issues I had with the SPI bus and trying to get it to work, and using the MDO3054 oscilloscope from Tektronix with its protocol decoders to look at the SPI bus and figure out exactly what was wrong. So if you're looking for the first one, then it's on my YouTube channel, and I'll link in the references to the other 2 videos that go along with this series in the comments. If you're not, and you're looking after a bit of information on SPI, then you're in the right place, and keep watching. Enjoy. Okay, so what we're looking at is the SPI data bus. I've got channel 1 of the oscilloscope hooked up to the clock, channel 2 of the oscilloscope hooked up to the chip select, and channel 3 is hooked up to the data. So what we've got now, what you can see on the screen here, is the 3 traces, the raw traces for the analog inputs of the scope are shown on the top. They're all referenced to the same 0. So what I'm going to do is I'm going to offset them just a little bit so that you can actually see where they change. So I'm going to bring the clock down a little bit, which is the yellow trace, and I'm going to bring the data line up a little bit. The DAC8734 is very typical of a lot of SPI DACs in that they have an offset register, which is effectively an address within the chip, which is typically a single byte value, which gives you obviously up to 255 registers, or a few registers and maybe some initial control values. And then you have, in this case, a 16-byte data packet that goes out. If you write that to the control register, obviously you can use it to control various aspects of that, like the GPIO and things. And if you write it to one of the DAC registers, then that becomes the value for the DAC registers, or the calibration registers, which are higher up. And the DAC registers start at offset 4, so you would have to have the addressing, which is the first byte that goes out, set to 4, and then obviously the second DAC would be 5, and then 6, and then 7. When you get to 8, you start getting into the calibration registers, and the 8, 9, 10, 11 are, I think, the 0 offset registers, and then 12, 13, 14, and 15 are the full scale registers. So we're not going to do that right now. What we are going to do is look at what and what we should expect to see when we output to DAC channel 0 is it should go out, and I'm outputting a value of 0 right now. It should go out as 4, 0, and then 0, 0, 0, 0. So let's just do that, and we'll see what happens. So I'm pressing the button now. All right, and there we go. So you can see the lines here on the oscilloscope. You've got the clocks for each of the 3 bytes clearly visible. The blue traces the chip select line. You can see there's a huge gap between the chip select line going down and the actual data starting, and the chip select line hasn't even gone up on this screen here. If I change the scale slightly so we can try and see where the chip select line goes back up, I'm going to crank it down a little bit, and we'll see if we can actually see where it changes. Let me just output that again. We catch a new trace. See, it still hasn't gone up there. That's one of the things I was saying to you about how slow this SPI interface software currently is. There we go. So that's, as you can see there, we've got the data happening here, and we've got this huge gap before it actually comes back to the application. Well, actually, it's not even back to the application at this point necessarily, but before it actually even undoes the chip select. And so at the lowest level, it's got this massive delay. If I turn the cursors on, we can actually measure that. Let's just let's just do it from the chip select. First of all, from the chip select to the start of the data here. Let's just expand that out a little bit. From the chip select to the start of the data, we have roughly, let's just get it on something. That's close enough. So we have about 1.5 microseconds, which is quite an eternity, really, from considering the Raspberry Pi is running at a gigahertz or something. That's quite a long time before it actually gets to output any data. Now, the issue is not so much that. I could live with that. What the issue is that I have is how long it's taking to actually, let's just expand this one out now to even just release the clock. Right? It's taking 69, 70 microseconds just to release the clock. And I did some measuring, and it actually takes about quite an amount of time per cycle when it's outputting. When I'm trying to output the sine wave, you can see how long it takes because the packet of data is actually completed being transmitted in roughly 4 microseconds odd is actually the time it takes to output the data, and that's the full 24 bits, sorry. But it's taking 69, so almost 10 times longer, well, way over 10 times longer, almost 60, 70, 10, 12 times longer before it actually outputs the chip select back to disconnected. So all that time, the software is not able to do anything else. So of course, that's consequently one of the reasons why when I'm trying to iterate through the sine wave table, it takes a long time and I get very low frequencies. But that's one of the issues I want to raise with Microsoft to see why these SPI drivers are taking so long to release the gap between the chip select start and the finish is just ludicrous here. I know it's a multitasking operating system and all that kind of stuff, but that really should not be happening like that. You should have the release like 5-6 microseconds, something like that, not 60 odd microseconds beyond it actually being able to collect any data. So if I just put that back up there again, and we'll just do the same thing just to get back to some real data. So we can see there that we're outputting register 04, which is right here, which is the one I said. That's the offset for the DAC register 1. DAC register 0 as far as the way TI describes it. And then we're outputting 00 to the register. If I actually output just value 1 to that register, what we should get is still 004 here. And then we output the most significant byte first and then the least significant byte. So we should get an 01 in this particular packet here on the trace. So there we go, and there we have it, the 01. Now the FFFFFF is the data that's coming back from the DAC output to the on the MISO output of the DAC. Yeah, the MISO, master in, slave out. So as with SPI, what's happening is as you clock things into a device, if they've got an output register and it's not disabled, it will actually clock data back out on the other side as well. Now, we're not actually using that, we're not even reading it, but it still happens in the background, so you really don't have much choice about it happening there. You just need to make sure your software is not going to cack if it sees it or something. All right, so that's reading register 1. So if I just, instead of 1, if I now output, say, 256, it should jump to the other byte. All right, and I'll output that now. And there you have it. So you've got 04, 01, and 01. You can see there's a little bit of a delay extra happening there. I'm not sure what these little ripples are that are happening every now and again. I think they're maybe from the switch mode power supply or something like that. I don't have a huge amount of decoupling on this breadboard. If you're running this on the actual DAC 8734 EVM board, you probably shouldn't get that kind of issues. You can, as I said, freely use this software or the Arduino Uno or Launchpad stuff as you wish, but or anybody else that gets this kit. Let me just flip to one of the other channels for a moment, and we'll go and output to DAC 1. So if I output a, let's just say a 32768 on that one, that should be now writing to register 5, which would be the first byte, and then you should see the value that I'm outputting on these two. So there we go. So now as you can see, it's 5 and then 8000 because I've outputted 32768, which of course is the 16th, well 15th if you start from 0, but 16th bit being set on the data. And if I output 65535, then you'll see it being FF. And if I just quickly flip through the other DACs, you see that's the channel 3, and you see it go to 6. I've outputted 32767 for that one. And if I go to DAC 4, you'll see let me just output 255 to that one. You'll see it should be 0FF, and there you go. Now obviously if I'm writing to the control register, so I'm doing things like powering down channel group A, you'll see that it'll actually output to the control register which is reference 0, and you can see now that it's outputting a 0, a 13, and a 0. and I've got 000 coming out in this case. When I was actually outputting to a register, you saw that I was getting actually FFs, but now of course the data's changing a little bit, and I'm getting different things coming out. I'm just switching, toggling bipolar, unipolar, and you can see there that I've got control register 1200, control register 1300. So there's a bit being set and reset depending on the mode as I go in and out of unipolar, bipolar. And if I go power up and down, you'll see that I've got an 03 or a 13, and the 13, the 1 on the first byte here is actually the bit that's telling me to power down on that group. And if I go power it up again, you'll see that that bit goes away. The actual 03 here is actually to tell it that I'm working in bipolar mode. So if I actually click both of them down to unipolar, you'll see that now I'm outputting control register 0000, which is now powered up, but I'm in unipolar mode. So both of my DVMs now, or my channels, would go from a 0 to 10 volt scale instead of -5 to +5 scale, based on how I've got this currently configured. So if I output 65535 on channel 1, I get 0 because I'm sitting in unipolar mode, as I said, sorry, bipolar mode. If I output 0, it should basically stay the same because 0 and 65535 are both the minimal values based on 2's complement. But if I go 32768, I should get -5, which I do. And you can see that going out on the register there. And if I output 32767, I'll get +5 on the DVM, which I am. I know you're not seeing that on the screen here because I'm showing you on the oscilloscope actually as we're capturing this. Now, I mentioned at the beginning of the video that I actually had an issue. And one of the things that I was doing, previous videos with talking with SPI devices, and I had some ADCs and things like that, also from Texas Instruments and also from Maxim and stuff, and I was using those in what Microsoft had. Well, actually it's not just Microsoft, it's part of the SPI standard. In mode 0, what it's doing is it's flipping between mode 0 and mode 1. Mode 1 is what works with this DAC. Mode 0 didn't work. And what it did was it basically flips the polarity of the clocking edge. It changes the edge that clocks the data into the chip. So in mode 0, it's using the rising edge. In mode 1, it uses the falling edge of the clock chip to clock it in. And obviously that could be quite significant. I don't know if I can do that on here, but let me see if I can capture a slightly better resolution picture on the oscilloscope and actually show you. I'll dynamically flip the software and change the edges, and we'll see if we can actually have a look at it to see if we can see any differences. Alright, so what I've currently got is a snapshot on the oscilloscope of the Raspberry Pi set to output a mode 1 SPI signal. And what you can see here is that the data, which is the purple line, comes up along with the positive edge of the clock, which is the yellow trace. And it's with mode 1, I have now actually confirmed this. Mode 1 uses the falling edge of the clock in order to clock the data in, not the rising edge. And as you can see here, the data comes up. Now what I'm outputting is 255, so the first byte is 0, which is why the data is low down here, and you can see the clocks are happening with no positive on the purple line. And then it's 255 in the least significant byte here, where the data goes high for the period, and it's clocking in on the falling edge. So you can see the rising edge comes up together. You would never try and rely on the rising edge coming up together as far as clocking data in. And then you've got a 1, a 1, a 1, a 1, a 1, 1, 1, 1. And you see the last clock negative edge happens quite significantly before the data goes down to 0 again. But if you actually look at the data sheet here, which is how I managed to figure this out, you can see here, this is the clock. Alright, and you can see the rising edge of the clock is happening before the data bit is being set. Now these crossovers happen because they're saying that you can go either from 0 to 1 or 1 to 0. That's just a standard way of showing them. But you can see that the clock falling edge is what's happening in the middle of the bits for the data. Alright, So each time it's happening in the middle, and that's what clued me into the fact that this was happening incorrectly. Now what I'm going to do now is I'm going to change the software to use mode 0 again, and we'll have another look. I'm just trying to remember the what the actual code is for 10101010 on the data. So we'll just see if we can put that in a moment, and we'll see with a better with the actual data signal what the differences are. But for now I'm just going to change this to mode 0, and we'll do exactly the same screen capture, and you can see the difference. So notice that the rising edge of the first clock, the data is changing, and it's the falling edge that's clocking in everything, and there's a bit of a gap between the last falling edge and the change of state back to a 0 again. Alright, so what you can now see on the oscilloscope here is a mode 0 trace. It's the exact same byte of the sequence that I'm showing you here. And what you can see now is that the data has changed to a positive value earlier on in the sequence, and the clock, because it's mode 0, it's the rising edge of the clock now that says that I want you to read the data on this rising edge. And so even though my controller, which is the Raspberry Pi, is now working in mode 0, of course my device, which is the DAC8734, it still wants to work in mode 1. So the Raspberry Pi is outputting, saying 1 on the positive edges of each of these. Alright, and there's 8 of them, of course. But on the negative edge, the DAC8734 is going to be clocking its data in. Even though the Raspberry Pi is clocking the data out in the positive, it's clocking in on the negative. And you can see here that this last bit of data, and we happen to have a nice 255, which means that the data line is staying high for the whole period, is clocking down at exactly the same edge as the clock is, which means that that's very risky, because you don't know particularly which threshold the clock line is going to say, oh, take the data, versus the data line differentiating between a 1 or a 0. So if they're slightly off, that could actually completely screw up, and it's very, you know, it's temperature and the volts that you're running it at and all sorts of things can play a part in actually screwing you up as far as reading the data in properly. If you want to output 101, 101, then you need to use decimal 170, and if you want to output a 16-bit equivalent, then you need to use 125252. So what I'm going to do is I'm going to output now 125252 to the register. For some reason my software is not, oh there you go, beautiful. So that's a mode 0, 10101. So you can see there's a 1, a 0, a 1, a 0, 1, a 0, 1, a 0. And you can see here that the clock, the chip, wants to clock in the data on the negative edge, but that's coinciding with the data itself falling down too. So like I said before, you got a 1 and it's clocking down, then you got a 0 here, but look at this one. The data is now coming up because the master thinks that it's only going to clock on the positive edge. It's quite happy to change the data line on the negative edge to the new value, which is going to be a 1, because it knows it's going to clock it out to the slave device on the negative edge. But the slave device in our case, which is the DAC8734, it's taking the negative edge to clock the data in. So now you've got the data going positive, the clock going negative at the same time. You tell me that you can guarantee what that's going to read, whether it's a 0 or a 1. It's going to be completely random. I mean, it may be over a short period of time, it may be predictable, but you know, with temperature and various other things, it really is unpredictable. You cannot ever be sure of what's actually going to happen there, and that's a mode 0. Now, if I actually change this now back to mode 1, then you'll see that now it will clean everything up, and you've got both the master and the slave working together in the right mode. Oh, I just figured out why the previous 16-bit value wasn't working. I was using a programmable calculator to, in programmer mode, to figure it out, and I actually read from the octal, which is 125252, and the actual value I should have inputted was 43690, which is the decimal equivalent of AAAA hex, which gives me the 10101010101010, etc. So I've just output that now, and what you can see on the oscilloscope now is the mode 1, which is the correct mode for the chip that we're using, output. And you can see here the yellow trace again is the clock, and the purple trace is the data. And you can see that the data and the clock change at the same time on the rising edge of the clock. But it's the negative edge, which is right in the middle of the data here, which is actually setting the locking the data in. So you can see it's had a chance to stabilize. Yes, it's raggy top, but it's well above the thresholds for the inputs of the device, and then it's going the negative edge of the clock to say, okay, take that piece of data. And in this way, it's actually working very, very reliably. And you can probably up the frequency. Right now, I think I'm running this at about 10 megahertz right now, and it's working perfectly happily. If I up this to even probably 20 megahertz, because of the fact I've got flying leads coming out of the Raspberry Pi and things like that, it probably doesn't want to really, it doesn't know about wanting. It wants to work very, very well, but it's not going. So if I go up to, say, 20 megahertz clock and run this again, just started it up now. Let's see what happens here. One of the problems with, obviously, I've done previous videos on time domain reflectometry and stuff like that, and length of wires and having connections and various other things connected with reflections on the end when they're not properly terminated and things can have a huge impact at high frequencies. So of course, the higher speed that you clock your data lines at, the bigger problems you're going to have when it comes to reflections and things like that and corrupting your data. So I don't know how far you can push flying leads like this, and maybe I'll do another video on experimenting with it and everything. But for now, I've just upped it to 20 megahertz instead of 10. So let's just see what this looks like. 43690. You can see there on the display that the square waves have now. You can see the clock has almost turned into a sine wave because of capacitance and inductance at the wires and things like that. It's completely lost its flat tops. Now, in this case, because the data is actually wider, it probably will still work just fine. If I actually power up my meter, I can tell you, I'm not going to change it from the scope, but I'm not sure what value I'm going to get there. But if I actually put in some other values right now, so let's put in 0, and that's actually, yep, that's still working just fine. Let's give me 0 volts. And if I put in 65535, it will give me the 10 volts. Yep, it does. And if I put in 3276, let's just say 5, just for a random numberish, and that's giving me roughly 5 volts. So even though it's the clock is almost a sine wave, you're still able to clock that. So that's basically running this thing at 20 megahertz. So that's not too bad. Now, obviously, 20 megahertz doesn't actually mean squat if the delays between each data packet, which is the 24 bits, takes 60, 70 microseconds before you're even able to remotely try and output your next byte again. It just isn't gonna cut it. And if I actually just run, what I'm going to do is I'm going to run one cycle of the sine wave on channel 1. It's going to do a few things on the scope here. Let me just see if we can even capture anything. Well, it is, but anyway, it's telling me that it's taking 46 milliseconds to do 256 steps, which is just one cycle of the sine wave. And that actually, if I just change this to standard mode on my calculator, 46, so say 47 milliseconds, because it's near 47. Divide that by 256 steps is basically 18 microseconds per step. That's just nowhere near fast enough considering the fact that it is a 1 gigahertz processor that's running this. Anyway, as I said, I'm still going to raise this with Microsoft and say, hey, what gives with the speed of this thing? You should be able to run a tight loop way, way better than that. And it's not even the loop. If I actually take out the call to the SPI, it can run this entire loop with 65,000 odd iterations in about 30 milliseconds, which means that you should be able to get several kilohertz of sine wave out or more from the Raspberry Pi if the SPI bus was working more efficiently, but currently it's not. Now, that's not a showstopper, of course. You know, you can use a microcontroller as your physical interface if you wanted to. If you wanted to be able to produce some high frequency signals and things, you know, you could offload the work of driving the signals to a microcontroller where it will be better apt at doing that tight timing and consistent timing, and just have the control mechanics in the Raspberry Pi. But in this case, what we're trying to do here is, you know, I would at least be able to expect to be able to get a few kilohertz of a sine wave out from a Raspberry Pi using the SPI bus to a DAC or something. Because if you want to actually output even to an LCD display and play video, I know that under Linux you can play MPEG videos and things like that out to a SPI connected LCD display and get full standard 30 frames a second whatever refresh rate on those displays, which means that the SPI bus must be running at a blazingly fast speed. Now, Windows 10 right now, what I'm seeing is that's not going to happen. Microsoft is going to have to get their act together and fix the driver for this to be able to make that more optimal, and I'm sure they probably will. Just the current version that I'm using is not supporting it. Now, maybe in a couple of weeks when the new versions come out, this will be fixed, and we will actually revisit this and have a look at it at the time. As far as using this to control, say, a power supply, for instance, which is why I'm actually looking at this DAC in the first place, I'm not using the Raspberry Pi or whatever microcontroller at this level as far as an interactive feedback as part of the feedback loop for controlling the power supply. I would use it to set the reference levels, and even if you wanted to have some kind of stepped load performance kind of metrics being put to a battery or some power supply or something like that, you could still do that, because even if it's running at just a few hundred hertz or something, I'm trying to simulate a sine wave. But if you're doing a square wave, you're going to be able to do that at a much, much higher frequency. But if you're actually trying to use it as an arbitrary waveform generator or something, then currently the Windows 10 software is not going to cut it. But if you want to use it to control a power supply as far as setting your set points and everything else, and having a somewhat static HDMI screen with a touchpad or something else like that. I haven't touched on doing software yet to talk to an LCD screen. I will be doing that very shortly, and maybe integrating with a touchpad and things. I'm slowly increasing the libraries that I have written. Currently I've got about 4 or 5 different DACs and ADCs in the library that's in the software that's going to be made available even at the end of this video that you can download. And I'm going to continue expanding on that, and you just use it as whatever you wish. But as you can see here, as far as controlling the SPI devices are concerned, one of the important things is read the data sheets, make sure you know what mode the SPI device is going to work on. I just assumed that because of the previous TI devices and other devices I've been using worked quite happily on mode 0, that this is going to work happily on mode 0 as well. And of course it didn't. And I went back to the data sheet, and coupled between the Tektronix MDO3054 Oscilloscope with its SPI logic, I was able to actually see what was happening there, and I was able to compare that to the timing diagrams that were provided for the data sheet for the DAC 8734. And at the end of the day, it's like, oh, stupid. Okay, let's change it. Quickly reviewed what the SPI different modes did. Discovered that mode 1 was the one I wanted, not mode 0, and then I changed that, and then everything worked. Now, because of the way the Raspberry Pi with Windows 10 works, you can actually have your different SPI devices running in different modes. It shouldn't actually matter because you create each instance individually. Now, the way that the Raspberry Pi is created right now, you can actually only have 2 base SPI devices, one on chip select 0 and one on chip select 1. I haven't played around with anything beyond that. I'm sure you probably could include something together, but really 2 SPI devices is probably more than enough when you consider that you've got I2C available to you as well. Anyway, so that basically concludes the physical look at this and the actual testing of it. So what's going to happen next is we're going to have a quick look at the software so that you can actually understand what I've done there. Alright, so I guess we're off to the computer.